Swayam Prabha. Digital India. Educated India.
Next speaker is friend Jagadisan from IIT Madras here. Please.
So, very good afternoon to one and all. Hope I'm audible. So, I am Jagadisan. I'm a research scholar in Department of Chemical Engineering. So, my primary research focuses on identifying crucial challenges in identification of system identification of biological process. We are all aware that when it comes to system identification, there are three crucial stages. Like we generate data, we have to select model, and we have to estimate the parameters. And model selection being one of the crucial challenges, and when it comes to systems biology. So there is a very interesting paper by Baba and team. They highlight important challenges in system identification of biological process, where they claim that model selection is one of the three classical problems. And why it is important or why it is difficult when it comes to model selection of biological process. One is the approximate nature of models. Or not all biological process or not all the biology driven equations adhere to the process completely. The second is existence of multiple hypotheses. And the factors that influence model selection, particularly in systems biology, are goodness of the predictions and goodness of the parameter estimates and biology of the process. So, another important aspect is why do we need to think beyond AAC and BAC? We all know AAC and BAC are great. And they've been very popular and used widely in the domains of AI, ML and system identification and time series modeling. But why do we need to think beyond AAC and BAC? AAC and BAC attempt essentially to strike a balance between goodness of fit and parsimony, basically how good the model is fit to the data and the number of parameters. But when it comes to biological processes, more than number of parameters and goodness of it, what is more important is the biology of the process. Am I able to estimate crucial parameters? So it does not guarantee anything about the goodness of the parameter estimates, how good the parameter estimates are. So the first point is that they do not guarantee any goodness of parameter estimates. And number two is, in most biological process, as I said, precise estimation of certain parameters becomes crucial. For example, in PK, PD or QSP models, precision of the estimates play an important role. So that brings us to the problem statement. Given a set of model structures and a data set and priors of the parameters, how do I choose the best model that explains the data? So we proposed in our previous work in a new index of information gain in the Bayesian framework. So what this information gain is based on what is known as a Bhattacharya coefficient, which is a statistical measure which quantifies the distance between two statistical distributions. And this information gain has two important features. One is when it comes to Bayesian framework, when you compute the Bhattacharya distance between the prior distribution and the posterior distribution of parameters, it quantifies the precision of the it actually signifies the precision of the parameter estimates. And number two is information gain for parameters that are sensitive is more than the parameters that are insensitive. These are the two important factors that motivated us to take this measure and apply it to model selection. And this is a visual illustration of the information gain. So if we see in the first figure, the information gain is approximately equal to 1 when where you can see that the pink one is the prior distribution and the blue one is the posterior distribution. And if the posterior distribution actually shrinks and the information gain is almost maximum. And when the posterior and the prior parameter distributions are identical, then the information gain is 0. And if they are in between, it's between 0 and 1. The primary idea here is when the information, I mean, like given a data set and prior parameter estimates and model structure, how much of information does the data set have about the parameter of interest? So this is the butterfly distance and coefficient. If you see equation 3, let us say f1 of theta is the distribution of the prior and f2 of theta is the distribution of the posterior. If f1 equal to f2, then Bhattacharya coefficient goes to 1, and then the information gain is 0. If they are different, it's between 0 and 1. So we have extended the Bhattacharya coefficient to multivariate distribution. So this equation 4 represents the multivariate Bhattacharya distance, and the equation 5 gives the Bhattacharya coefficient e power minus bd. We can see that the distance is actually symmetric. Unlike Kullback-Leibler divergence, this distance is actually symmetric. And here we show that the decrease or the increase in the information gain results in reduction of the parameter estimates. So the first case is straightforward. When the prior and posterior parameter distributions are equal, then the Bhattacharya distance is essentially 0 and the information gained is 0. If only one of the samples from the prior gets selected, which means that the variance covariance matrix goes to 0, which results in maximum information. So here is an interesting theorem that talks about its relationship with D optimal. When the mean of the prior and posterior distributions are identical, then maximizing the information gain proposed is equivalent to minimizing the determinant of the covariance matrix. That can be seen from the equation 10. And we propose one more measure to assess the goodness of the fit. We take all the parameter samples from the posterior distribution and compute equation 11 and 12. The 12 kind of signifies how precise the predictions are, while the Bhattacharya coefficient talks about how precise the parameter estimates are. And this is how we propose to do the model selection. So given a joint prior, a model structure and data, you do the Bayesian estimation and compute a joint posterior and compute the proposed information beta and the prediction uncertainty delta. These two components will tell us about, for the candidate models, how much is the prediction uncertainty and how much is the parameter uncertainty. And we illustrate this using a set of 2 compartment models, which is common in systems biology, or these kind of models are generally used in pharmacokinetic and pharmacodynamic modeling. So here we have a set of candidate models, and the equations are given below. And the true model, the data is generated from the model M1. And I have given the true parameters here, and the data is generated and noise is added such that the signal to noise ratio of the measured data is around 30, which is a very low signal to noise ratio. So here the results shows that the information gain for M1 is maximum and the prediction error for M1 is extremely low. So the method has successfully chosen the true model. The information gain index, beta and prediction uncertainty are maximum minimum respectively, as we see so for the true model. And another interesting aspect, when it comes to parameter estimates, there are certain parameters in every model that are stiff and sloppy. They are known as which means that they contribute more to the predictions. There are like sloppy directions, which are those are the parameter directions which contribute very less to the predictions. So here we can see that the parameter K01 and K21 are actually very sensitive parameters, and the information, the precision of those parameters are really good. So that is the reason why, if you can see among all the models, the model M1 has very high prediction and very high precision in the prediction, primarily because the parameters that are responsible for the predictions have been estimated with very high precision, which is not in the case of model 2 and model 3. And model 3 becomes extremely, it's poor primarily because the parameters that are responsible for the predictions are estimated, very far from the true data. The point estimates are quite far from the true data. Primarily, that is the reason why they have very large systematic errors. So the conclusions are that the proposed model selection method is based on the goodness of prediction, the parameter estimates. The information gain index of joint distribution minimizes the variance and bias of the basically sensitive parameters. We have numerical evidence for this in our previous paper, which is about to appear in IFAC papers online. And as a consequence, the prediction uncertainty is tightly bounded around the data points. The extensions are a new experimental design have developed for Gaussian priors based on this. And the information, these gain index have been extended to non-Gaussian priors. And a new experiment design method developed for non-Gaussian priors in the Bayesian method have also been developed. So, thank you.
Time for questions or comments.
You are comparing three models, right?
Yes.
But what kind of priors you use for the three models? Because the models are different.
Exactly.
You have what kind of the priors will be different somehow, or do you use a naive prior or whatever? Prior?
You mean to say you are talking about the distribution of priors?
Yeah. Each models are different, right? So for the priors, for the parameters, will be different. So what kind of prior you use in the three models?
All of them, the nature of the priors, all of them are essentially joint Gaussian.
Joint Gaussian of the parameters.
Joint Gaussian of the parameters, yes.
Any other questions? Yes, please.
So, Prem, just as a follow-up to the question that was asked earlier, I think it will be complete if you can specify, you only specified the family from which the priors are drawn. Could you be a bit more specific and specify if the variances were similar, prior variances, prior means are the same? Could you throw light on that as well?
For the simulation experiments, we have the prior means and prior variances were slightly varied, but not to a great extent, because we are looking. It's not much change from the true set of parameters.
I think the question, perhaps if I got it right, was in the spirit of ensuring that you're being fair to all the models. Am I correct? Right. So, I think if you can address that, were you fair to all the models?
Yes.
That's a point that you have to address.
Thanks to the speaker again. Thank you.